Okay, we are in section 15.1.2, insulators and conductors. So in conductors, in conductors, electric charges can move freely if an electric field is present. All other materials are called insulators. Glass and rubber are insulators. When these materials are charged by rubbing, only the rubbed area becomes charged, and the charge doesn't move to other parts of the object. On the other hand, good conductors like aluminum, copper, and silver have charges that can easily move over the entire surface of the object. If you hold a copper rod in your bare hand and rub the rod with wool or fur, it won't attract a piece of paper. This might make you think that a metal can't be charged, but if you hold the copper rod with an insulator and then rub it with wool or fur, the rod remains charged and attracts the paper. In the first case, the electric charges produced by rubbing easily move from the copper through your body and finally to ground. In the second case, the insulating handle prevents the flow of charge to ground. Semiconductors are a third class of materials, and their electric properties are somewhere between those of insulators and those of conductors. Silicon and germanium, shown in the photos, are well-known semiconductors that are widely used in the fabrication of a variety of electronic devices. Okay, charging by conduction. Let's think of a negatively charged rubber rod which is brought into contact with an insulated neutral conducting sphere. The extra electrons on the rod repel the electrons on the sphere, which creates local positive charges on the neutral sphere, as shown in the figure on the left. On contact, some electrons on the rod are able to move onto the sphere, as in the middle figure, neutralizing the positive charges. When the rod is removed, as in the figure on the right, the sphere is left with a net negative charge. This process is called charging by conduction. The object being charged in this process, in this case the sphere, is always left with a charge having the same sign as the object doing the charging, in this case the rubber rod. When an object connected to a conducting wire or copper pipe buried in the earth, we say it is when an object connected to a conducting wire or copper pipe buried in the earth, we say it is grounded. We can think of the earth as an infinite reservoir for electrons. In effect, it can accept or supply an unlimited number of electrons. With this idea in mind, we can understand the charging of a conductor by a process known as induction. Let's imagine we have a neutral conducting sphere that is insulated, which means there is no conducting path to ground, as in the figure. Now let's bring a negatively charged rubber rod close to the sphere, as in the top middle figure. What happens is the repulsive force between the electrons in the rod and those in the sphere causes some electrons to move to the side of the sphere farthest away from the rod. The area of the sphere which is closest to the negatively charged rod has an excess of positive charge because many of the electrons move to the other side of the sphere. Let's imagine we connect a grounded conducting wire to the sphere, as in the figure. Now, some of the electrons leave the sphere and travel to ground. Now we can remove the ground wire, as in the bottom left figure, and the conducting sphere is left with an excess of induced positive charge. Finally, when the rubber rod is removed from the vicinity of the sphere, the bottom right figure, the induced positive charge remains on the ungrounded sphere. Even though the positively charged atomic nuclei remain fixed, this extra positive charge is uniformly distributed over the surface of the ungrounded sphere because the electrons spread out. The charged rubber rod doesn't lose any of its negative charge because it never comes in contact with the sphere, and the sphere is left with a charge opposite that of the rubber rod. Charging an object by induction requires no contact with the object inducing the charge. let's see what we can do with insulators. In most neutral atoms or molecules, the center of positive charge coincides with the center of negative charge. But if there's a charged object nearby, these centers may separate slightly, which results in more positive charge on one side of the molecule than on the other. This effect is known as polarization. The realignment of charges within individual molecules produces an induced charge on the surface of the insulator, as we can see in the figure. This property explains why a balloon charged through rubbing will stick to an electrically neutral wall, or why the comb you just used on your hair attracts tiny bits of neutral paper. Okay, the next section we're going to talk about is Coulomb's law, but we'll end this right now.